Hello, Tiger Chemists! In today's video, I'm going to be covering Hess's law and also how it relates to heat of formation calculations. So far in class, we've talked about a couple of different ways that we can solve for delta H. We've talked about how we can do that using bond energies, and we talked about how we can use calorimetry. Now we're going to use Hess's law and also heat of formations. So Hess's law states that the change in enthalpy from reactants to products, or the delta H, is the same whether the reaction occurs in one step or in several steps. So that means that we can look at the sum of the different paths that the reaction can take to figure out the delta H. When we reverse a reaction, we need to make sure that we reverse the sign of delta H. If we multiply the coefficients by an integer or a fraction, then we need to make sure to multiply our delta H by that same integer or fraction. That all kind of sounds a little confusing. I think that it's usually easier to see this with an example. So I'm going to go through three. Here is my first example. It asks me to calculate the delta H for the following reaction using the information in the table below. You can almost guarantee that when you are given reactions, as we are in this case, and you're given delta H's, and then asked to find the delta H of another reaction, that you are going to use Hess's law. So what we are trying to do is take reaction 1 and 2 and use those as puzzle pieces to build this reaction right here. Okay, here's how I like to do it. I look at the reaction that I'm trying to build, that I'm trying to calculate the delta H for, and I look at one of my reactants. And in this case, I'm looking at NO2. I see that NO2 has a coefficient of 4. Okay, so I look at my two reactions that are given to me, and the only place that I see NO2 is in the second reaction, and I see that its coefficient is 2, and it's in the products. But in the reaction, I need it to be in the reactant side. So what I have to do is reverse this reaction, and I also am going to have to multiply by 2 because the coefficient is 2 when I need it to be 4. So I'm actually going to rewrite this. So like I said, I'm going to reverse it and multiply it by 2. So that's going to be 4 NO2 goes to form 4 NO plus 2 O2. Now, like I said earlier, when I reverse a reaction, I have to change the sign of delta H. And when I multiply by a number, I have to multiply delta H by that number. So I'm going to change the sign of my delta H, which was this, and I'm going to multiply it by 2. So that ends up with 228.4 kilojoules. Okay, and that is positive because we reversed that reaction. Okay, well that's cool. That gives me that, but I have to look at everything else as well. So next I look at the N2O5. Okay, the only reaction that has N2O5 is the first reaction. And so I find that it is in the product side. That's what I need, where I need it to be. So I do not need to reverse this reaction. I'm going to keep it as is in terms of the products and the reactants. But the coefficient needs to be 2. And so I need to multiply this reaction by 2. I should have done this on the last one as well. Okay, so for reaction 1, I need to multiply all of my coefficients by 2. Okay, and what I usually, okay, so for my delta H here, I'm trying to get ahead of myself here. I multiplied my delta H by 2. Okay, and what you need to do is you need to make sure that the two reactions add up to the overall reaction that we are trying to build. So what I'm going to do is things that are on the same side of the arrow add together, and things that are on opposite sides of the arrow cancel each other out. So if I'm looking at this here, I see that on both sides of the, I see that on both sides of the arrow, I have 4 moles of NO gas. So they cancel each other out. I also see that oxygen kind of does that, right? There's 2 here and there's 3 here. So I'm going to cancel out 2 of them, leaving 1 O2. Okay, so then when I write out my final product here, or my final reaction, I have 4 NO2 gas plus O2 gas yields 2 N2O5 solid. That matches the reaction that we are trying to build. Okay, so for my delta H, I can add these 2 values together. So 228.4 plus negative 447.4, and I end up with negative 219.0 kilojoules. The satisfaction that you get when it all adds up and cancels out is fantastic, and I love it. Okay, so that is our first example. Our second example is very similar.
If you are a faculty member and have your car parked in the band parking lot, if you could please move it. The band is trying to rehearse. Again, we need cars moved from the band practice field. Thank you.
Okay, so here I just took this and it was split onto 2 different pages, and so I just put it onto one page for me so that I could show you it a little bit better. So if you're looking at your book, it may be split in 2 pages, but I have it just so you can see it all on the screen here. So in this problem, we are trying to build this reaction. This 2C plus H2 gives me C2H2, and we're using the 3 reactions that are given. Okay, so I'm just kind of looking at this, taking a look, and I see that I have 2C as one of my reactants. So I look at where I see C in the 3 reactions that are given. And the only reaction that has it is the second reaction. And 2 questions I need to ask myself. First is it on the correct side of the reaction arrow? And it is, right? It's on the reactant side. So I don't need to reverse it. Second question is the coefficient the same? And in this case, it's not. So I need to multiply that by 2, which means that I also need to multiply my delta H by 2. So I'm going to rewrite reaction 2 to be that, and I'm going to multiply my delta H by 2. Okay, second thing I see is H2, and my other reactant is H2, and let me find it here. Okay, the only reaction that also has H2 is reaction 3. First question I ask myself is it on the correct side of the reaction arrow? And it is. Second question I ask myself is, does it have the correct coefficient? And it does. So I actually don't have to do anything to reaction 3. I can actually write that out as is. Which means that its delta H would also remain as is. The last part of this is recognizing that there's C2H2 in the product. Okay, the reaction that has C2H2 is reaction 1. first question I ask myself is that on the correct side of the reaction arrow? And it's not. And so I need to reverse this reaction. Okay, so I need to reverse this reaction. Second question is the coefficient correct? And the answer to that is yes. Okay, so the answer to that is yes. So I don't have to multiply it by anything, but I do have to reverse it. And since I reverse it, I do have to change the sign. Okay, so I reverse this reaction. This is reaction 1. And I'm going to change my sign. And I end up with that. So now the moment of truth, right? Do my reactions build to the reaction that I'm trying to solve for the delta H? So let's take a look. Okay, let's see what I can cancel and what things need to add together. So I see that I have H2O in both the reactants and the products, 1 mole on both sides. So those cancel out. I also see that I have 2 moles of CO2 on either side of the reaction arrow. So those also are going to cancel out. And then this one might be a little bit weird, but I have 2.5, right? There's 2 and there's a half. So 2.5 oxygens on the reactant side, and I have 2.5 oxygens on the product side. So oxygens also cancel out. Okay, in the end, that leaves me with 2C plus H2 yields C2H2. Oh, that is what we wanted, right? So that means that I can go ahead and move forward with adding my delta H values together. I feel like I did not put that in my calculator correct, but I hope I did. I got negative 2372.5 kilojoules. That is super exothermic. Okay. So that is our second example. All right, so I said we were going to have a third example, but I take that back for now, at least. I found a couple of errors in it, and so I'm going to go ahead and have us look at that in class after I fixed it. Okay, so the last part of today, I'm going to talk about enthalpies of formation. And so I'm going to show those as delta H sub F. And so this is a change in enthalpy that accompanies the formation of 1 mole. That's incredibly important. The formation of 1 mole of a compound from its elements with all the substances and their standard states at 25 degrees Celsius. So we're going to have to talk about that. We're going to have to unpack that a little bit in this video. The degree sign on a thermodynamics function, which is this right here, that degree sign indicates that the process it represents has been carried out at standard state conditions, which means that for gases, the pressure is 1 atmosphere. For solutions, the concentration is 1 molar. For a pure substance in a condensed state, like a liquid or solid, the standard state is the pure liquid or solid. And for an element, the standard state is the form in which the element exists under the conditions of 1 atmosphere and 25 degrees Celsius. Okay, so basically, when we're in a room, like at room temperature, and we're pretty close to 1 atmosphere, what state is that element in? Okay. So values for delta H of formation can be found in a table or an appendix at the end of a textbook. I will always give you these values if the problem calls for it. If you see that you are given delta H of formation values, it's usually a pretty good clue that this is the formula that you are going to need to use. This formula can be found in your AP reference materials. So you will always have access to this formula. However, it is in your best interest just to know it and know that you can do products minus reactants in order to figure out the delta H of the reaction. One thing that is incredibly important is that you recognize that the delta H of formation value for the most stable form of any element in the standard state is 0. What do I mean by that? I mean, for example, that if we were to have iron as a solid, which is how iron would show up in elemental form, then its delta H of formation would be 0. And that would be the same for pretty much all of these guys up here on my periodic table, right? But there are some that we know, like oxygen, that its stable form is as a diatomic gas. And so that is O2 gas, for example. Remember that our diatomics, just as a quick reminder, are Brinkelhoff, or bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. All of these show up as diatomics, not all gases, okay, but they are all diatomics. Okay, so here is the standard enthalpy of formation for methanol. What you'll notice is that methanol is the product. You'll also notice that there's only 1 mole of methanol. That's incredibly important. It has to be 1 mole for it to be a standard enthalpy of formation. And then you notice that this is in its standard form, this is in its standard form, and this is also an element in its standard form. Okay, so this is how I would write out the standard enthalpy of formation for methanol. This is the heat of formation or enthalpy of formation for methanol. Some people look at this and say, why do I have a 1/2 in front of O2? And that's because that would be what would be required in order to have a balanced equation that puts 1 mole in front of methanol. So if I were to write a balanced equation for the standard enthalpy of formation for aluminum oxide, I want to make sure that my product is aluminum oxide, okay, and we'll say it's solid, okay? That's just kind of what I'm assuming here. Okay, so we have aluminum oxide as my product. I have to make sure that I make it 1 mole, okay? Now, in the elemental form, I have aluminum, and I also have oxygen. Okay, so I have aluminum and oxygen.
I don't think I've ever seen you without a mask.
I know, I'm cute, right?
That's good.
Mm-hmm. Okay, so that is a solid, and the O2 is a gas in the standard state. Now, I do have to make sure that I balance this equation. So to balance it, I'm going to put a 2 in front of aluminum. And then in front of oxygen, I'm going to put 3/2. So if I do 3/2 times 2, that gives me 3 oxygens, which would balance out my oxygens. So this would be the balanced equation for the standard enthalpy of formation for aluminum oxide. Okay, here's an example of a heat of formation problem, and I'm going to show it in 2 different ways. Okay, one way is the long way, which goes and gives us a little bit more practice with Hess's law, and the second way is the easy, faster way that I would prefer you work the problem. Okay, I've also put it onto this page here just so that I have more room to work, because like I said, I'm going to show this in 2 ways. The second way is the faster way, if that's the way that you want to include in your notes. Okay, so what I see in this problem is that they want me to find the delta H for this reaction, given the heat of formations of 2 of the different compounds in the balanced equation. Okay, so what I'm going to do is I'm going to write out the heat of formation reactions for both of these. So the heat of formation for Fe2O3 would be Fe solid plus O2 gas yields Fe2O3 solid. Okay, once again, I do have to make sure that this is balanced, and I would do it like that. Okay, I'm going to do the same thing, and I'm going to put off to the side here that my delta H of formation for that reaction is negative 821.4. I'm going to do the same thing for aluminum, oxide, which this is the same one that we wrote before. Okay, so that is the heat of formation for Al2O3. Now, I can use these two reactions with the heat of formation value that is given and build this reaction right here using Hess's law. Okay, so maybe you should pause me, see if you can work that, and then unpause me and listen to that explanation. Okay, so just like before, I have Fe2O3. Here is Fe2O3. So I would need to reverse this reaction. But one thing that I do see is I see that the coefficient is correct. So I am going to reverse that reaction. So it's Fe2O3 is going to go to form 2Fe plus 3/2 oxygen gas. Since I reversed my reaction, I'm going to change my sign, right? I'm going to multiply that by -1. For the second one, I know that Al2O3 needs to be a product, and it is, so I'm not going to change anything about this reaction. Okay, like I said, I didn't change anything about it. Okay, now what I notice here is that I have 3/2 oxygen on both sides, so those are going to cancel each other out, leaving me with Fe2O3 plus 2Al yields 2Fe plus Al2O3, which, that is what I want. Right? That is the reaction I'm trying to find the delta H for. So at that point, I would just add these delta H's together, and that would give me my final answer. Okay, that's the long way. Okay, that's why the way I'm about to show you works. Okay, that's the chemistry behind it. But let me shorten this up for you a little bit. Okay, the shorter way of looking at this problem would be to use this equation, which is the sum of the delta H of formation of our products minus the sum of the delta H of formation of our reactants. Okay, well, let's work that out. So we have the delta H of reaction would be equal to, well, let's look at what our products are in that reaction. The products of that reaction were 2 moles of Fe, so I would use the delta H of formation of Fe, and then also 1 mole times the delta H of formation of Al2O3. Okay. From that, I am going to subtract my reactants, which is 1 mole of delta H of formation of Fe2O3 plus 2 moles times the delta H of formation of Al. Okay, so here's where I only gave you 2 delta H of formations. So how do I know the delta H of formation of iron and aluminum? And here's the answer. They're 0, right? They are in the standard state. So when I do this calculation, those are just going to be 0. So my delta H of reaction would be 2 times 0 plus 1 times the heat of formation of Al2O3, which is negative 1675.7, minus my products. And so my product here was Fe2O3, If I look at that, that's 1 times negative 821.4 plus 2 times 0, right? Because aluminum is an element in its standard state. So this ends up being negative 1675.7 minus negative 821.4. And what do you know? We get the same answer that I just got without me having to do all of the shuffling that I was doing before. All right, so that is all that I have for you in this video. You want to make sure that you've gone through and think, what questions do you have for me in class? And then we will spend time practicing this and getting much better at it. Bye, y'all.